I don't know if I want to do that quite yet. We'll have this just in case. So what I'm going to start with today is actually a completely different slide deck that was not made by me, but instead made by the grader. As the grader has been going through grading everything from the first assignment, there were a bunch of outcomes that I thought, well, he thought I should share with the class. And then through talking with him, I think there are a few things that are just worth mentioning with regards to why specs are the way that they are, things that you can do wrong as you submit, and what makes the grader's life a little bit more challenging, and why and how that's embedded in the spec. So the first one that we're seeing here is a nested folder name. So these are all real submissions. If this is yours, you don't have to own any of that, but just making sure that these are the kinds of things that can happen and what the grader needs to do as a result of that. So if you have a folder inside of a folder inside of your zip, then when the grader writes a grading script that anticipates that there's going to be one folder and then the files that it's looking for, that script doesn't run.
Oh.
So we're saying we want there to be the folder inside of that bin file.
Yeah. Okay. Yeah. In this case, there is the folder inside of the folder with the stuff inside of it. Another one is watch your file names. If you are selecting the .txt and then you type in something.java, it appends the .txt to the end of it, and it's not actually read as a Java file when we go to open something.java. Oops. Same thing for a .pdf. If you're saving things, make sure that you're aware of file types and make sure that the file that you submit is actually the type that you think it is. This is a relatively easy fix, but again, it's something that the grader has to go manually do to edit the name of your folder once their grading script stops working for some reason. Couldn't find that file, it doesn't exist. Why? You go to look and you find something like this. Another example. The idea would be to name your stuff correctly. What do these things mean?
That's BSC.java, which is an acronym for binary tree.
Yeah, that's fine. But what do these classes represent? If you're submitting 3 classes, the name of the class should tell you the creative submission idea was for the name of the folder so that we wouldn't have duplicates on the folder name. With regards to the classes that you submit, they should represent what that file does or is in some capacity. Here's an example of what the grader's script looks like when it runs on something that is log n. So when we say that we're looking for insertions or deletions running in logarithmic time, you can see when you run this yourself that it should run in a reasonable amount of time. If it's logarithmic and you throw 10,000 or 100,000 insertions at it in a loop to just build a very large tree, this is what logarithmic complexity looks like for each insertion and deletion. We're looking for n log n in terms of the n being the 10,000 insertions or the 100,000 insertions. So if that's the case, this is what a logarithmic time process looks like. Very nice. Don't pay attention to what the grader named these files. Here is an example of what happens when you implement it not logarithmic. The grader gets to sit around for a while. And in fact, the grader is currently going through a couple of submissions where the timeout for the unit tests that he wrote is past 5 minutes. So we need to go figure out exactly what happened on this. So stress test your program. You can go through and analyze, am I calling something in a way that is logarithmic? Great. But the way to really test it is to throw a large-scale problem at it. You don't want to print any of these trees. Please don't print these trees. It's going to be disgusting and take forever just to print them. But run them without any printing, and you can see how long your code is taking when you stress test it. So here's an example of one that does not adhere to the time constraints. Another big problem is paying attention to specifications. So I did say you could plug and play an old binary search tree that you've used, but you would want to make sure that fields, especially publicly accessible fields or fields that are going to be used or called from throughout, as well as method names, etc., all adhere to the actual specs. So the specs are on top here. So the names of the nodes should be left child, right child, and parent. There is no parent here, and left child is called left, right child is called right. If we're writing unit tests that are manipulating the underlying nature of using your code, we can write a single script that does this for everyone's program at the same time, as long as there is consistency in what the publicly accessible material is named. If we anticipate that we should be able to do something like traverse a tree and determine that it's in the appropriate order, we should be able to see that these calls are not dot left, but dot left child, exactly as specified. Another example of it is even something like camel casing your method names is something that will cause us to have to go change the script to look for things like different capitalization, to look for writing that script, to look for changes in the API is a pain. And I'll give you an example of that here in a second. So this is what the grader's code looks like if your API is consistent with the API from the specification. This is how much work it takes for the grader to be able to do something like insert into your tree. On the other hand, if he can't rely on your API, this is the code he has to write.
Oh, a bit more.
So this is the actual code that we've used for this, and here's some annotation to it. So he has to do some work to figure out where the method is based on, okay, is there an insert somewhere within the class? Is there a method with the word insert in it somewhere? If so, call that method. So we have to write code that goes through and looks for keywords or looks for, we have to intelligently figure out how to dissect your code to find what you've called the method that's doing the thing that doesn't have an exact match to the name that it's supposed to. So you can do that. You can call via reflection. You can see if any methods in your entire class match a case-insensitive name and or the number of expected parameters. So these are all sorts of advanced unit test procedures, but it's something that if everyone adheres to the specifications, then it's not necessary to do this. This still saves time because we can run this generic test and not have to dive in and look at 10 or 20 different assignments to figure out what did each of these people name these methods. But it's much easier on the grader if everyone adheres to the spec, and the entire grading process is just writing and calling that.
Yeah.
Much easier. So this is not meant to shame anybody. I'm sure that this is something that most of you have never seen before or thought about the workflow that goes on behind the scenes, but it's just something that we can share, that we can all learn from as to why assignments have the kinds of specifications that they do. To give you an idea of what happens when we run this over everything, this is how long something can take. So the grader's response here or note in this slide deck is, I promise I'm working on grading the first coding assignment. This is evidence that this is ongoing, but his computer is held hostage for a while as we run all of these, as we're going through those that are less efficient and making sure that we have an approximation for the associated running time so we can dive into the code and look at why this is running at the time that it is, so we can provide real substantive feedback for how to improve. So that will be back to you in the reasonably near future, but just wanted to share kind of some do's and some don'ts with regards to how to think about. None of this will be held against you from a grading perspective. It's just for your knowledge. Yeah.
To clarify, in the zip file, you don't want another folder in there, right? You want the zip
You open it and then it's just Java.
It should be your project name. So it is one folder. If we go to that very first slide, this is a folder inside of a folder.
That's bad.
Yeah, so the zip would have been zipped into a folder. Inside of that folder is another folder. If you unzip into a single folder that has your project, that's great. If you unzip into a folder that has a folder that has your project, yes. Other questions about any of these?
You read any of the file name? Read it?
I haven't yet, but I occasionally get Discord messages from the grader with this one was hilarious. So I tend to see the best of, at least according to the grader's perspective.
So, in that case, once they're all graded, are we gonna go over who had the best?
I can at least share the ones that I've been made aware of, and or I can ask the grader to share his 5 favorites, something like that.
So for this assignment that's due today,
Yeah,
the specification like isn't as specific.
correct.
So is there like a specific way you want us to do it or?
No, in this case, it's easy enough to just run your main file, basically.
So you want us to include the main file?
We can, we're gonna have our own main, so you have your own class for this. We write the driver that goes through and just runs that.
Okay, so don't include.
Yeah, you don't need to for your own testing, whatever testing you've done. We'll have our own file and then we'll just run that.
Oh,
Can I have a similar question? One of our received file. Set file names, which actually static. Okay. File name.
Yeah, it can be a static input file name. So always expect that it's called input.txt and that's perfectly fine. And then we'll be looking for a file called output.txt. So make sure that you're not writing to output.txt.txt or any, just make sure the exact file name is as anticipated, and then the grader script will run very nicely on that.
yeah, just to be forewarned, the class that does have, well, my class for the global sequence alignment work rate did. It's not really mainstream, and I don't really think that's a big deal, but just warning you guys ahead of time. Could be a little challenging.
Won't matter.
I was confused, and I thought that, we wanted it to be a program that it just run on the file, like it doesn't need another class to call it.
Yeah, it does not.
Okay.
Yeah, it's gonna be something that we run your program that's going to look for input, and then our input will be substituted for all of our input test cases. So there's not too much spec for this because we're not calling the exact, everything is aligned within your program. Your program knows the names of everything. So all we have to do is run your program, as opposed to with the binary search tree that has more of an API to it, because we can, from an outside perspective, call each of those individual methods, call insert, call delete in an order that we want. So since we're interfacing with the names of your methods, then that's why an API is needed for that. Whereas for this, you have one program that does everything from start to finish. So we just have to start the process, and then nothing else is needed from our perspective except verifying the output. Other questions? Okay. We can dive back into we were just doing, and since PowerPoint decided to use so much memory that it crashed, I don't remember where we were. We were just starting to talk about depth first search, weren't we?
Yeah, we were.
All right. Questions on anything else from the class? I'll have office hours after class to, I shouldn't say help you get started at this point because it's due tonight, but I can help you get unstuck. Hopefully people are at least at a point where my input will help you to get things done by tonight, 1 to 2.
Will the new program be out today?
Bravo. We'll see. It depends on how far we get today. My best guess is we just won't have covered enough for you to get started on something. I would like to design it today.
Right,
But I'm guessing at this point, it's most likely that it's going to be something that's not due next week. It'll be due the week after. It'll be a little bit larger in scope. But that way I'm not having something due a couple days before an exam for material that won't necessarily be directly on the exam in terms of an implementation.
Another question about this, I mean, it said that we are assuming correct input. So I just realized that like, didn't really do a whole lot of error handling. Wondering,
You
should I-
don't need to do error handling for anything like the file structure. So if the file is not named input.txt, doesn't matter. I don't expect your program to figure that out. It's a user error on the setup.
actually, my program with IntelliJ was very insistent that I tries to catch these like any like exception errors for some reason. So I had to implement that. I hated that, but it was nothing to be done.
If it's a matter of something like the file exists that you can easily handle with just throws file not found exception on the method that is reading in the file. That's
I actually just did a try catch type deal.
that works too. But yeah, I'm not going to be looking for a program that manages if the input file doesn't have the exact specification, does it crash nicely, etc. That doesn't matter. Everything that we test is going to be the file is going to have the appropriate name, the appropriate layout. There isn't going to be any fun business in the file itself. By edge cases, I mean things like if one string is empty, if both strings are empty. What is the optimal alignment between an empty string and an empty string? It is a score of 0 and not a crash. Score of 0 with 2 empty string alignments. So error handling like that's based on what weird side cases can I throw at? What happens if the gap penalty is positive and the match bonus is negative? Is there anything that you're doing that's hard coding and expecting values to be positive or negative? It should work in a general case where a match and a mismatch and a gap are arbitrary numbers. And it should find the appropriate alignment given those values that are in the file. So I'm looking for your program handling those kinds of cases, which it should happen by default, unless you are making some kind of assumption and hard coding something in your program that's saying that this value needs to be positive. If it's not positive, there's something wrong. We don't know. It's work in general. Anything else? Okay. Back to depth first search. So when we very briefly talked about this yesterday, we had seen this in our traversal of a binary search tree. If we're doing something that is in order in a binary search tree, we're using depth first search in a tree. But we need to generalize the idea of depth first search in order for it to work on a graph. In a tree, we always know, at least in a binary tree, we know there's a left child and a right child. So when we're depth first searching that, we can call, say, handle the left subtree, then print the value that's at this node, and then recursively handle the right subtree. But in a graph, we don't know how many neighbors this node is going to have. We could have an arbitrary number of neighbors. So we can't specify something like a left node right because there's no concept of left necessarily in a graph. So what do we need to do in order to be able to apply this idea to graphs? We've already talked about this a little bit, but we needed a way to order nodes to determine the order to recursively search. For a graph, this is going to be exactly the same general idea. We need some order to determine how we're going to recursively search paths of this graph. So we could do things like order the neighbors alphabetically or numerically, something that says there's a natural order to these neighbors that we're going to explore in that order. In the same way that you would write a comparator for an object. What is it that these vertices are storing? How can we sort our neighbors to a low to high via something. So here we have a graph, but let's imagine that we are depth first search, breaking our tree down, and we're going to, starting at node A, depth first search this graph. Go ahead and on a piece of paper or talking to some neighbors, think about what is the order that these nodes are visible. So what we're going to do, we explore the node, and then we're going to recursively call this on its children. But we're going to recursively call it on its children in the order that is alphabetical. But again, we're doing this depth first. So we're going to explore the child before we come back and explore the next element in the parent node, if that makes sense. Question is asking is basically if we wanted to get to each of these nodes, so from A is straightforward, we start there. If we want to get to B, we're going to be exploring nodes depth first in alphabetical order from what's available from the current node. So what is the sequence of nodes that we need to do in order to get to each node? So if the query node is B, we just explore A and then B. If the query node is C, what is the depth first search order of the nodes that we visit before we first reach C? Let's walk through that one real quick, just to make sure that we're on the same page. We're going to expand A, which says we're going to add to recursion. It's kind of a recursive queue. We're going to add B and then D and then E. And we're going to visit B, the first one of those. But before we go back to A, we're going to add E and visit E immediately. From E, we're going to visit, there's only one outgoing edge, F. From F, there's only one outgoing edge, C. So that's the order that we go, A, B, E, F, C, because we immediately hop to the first child alphabetically for that node. And then we look at everywhere we can get from there, hop to the first one alphabetically. Look at everywhere we can get from there, hop to the first one alphabetically. And then if we ever end up with nothing that we can do, or everywhere we could go is already something that's been visited, then we will backtrack and explore the next one. So that's the path we take to get to C. Does that make sense to people?
Yeah, it makes sense.
How would we get to D?
What, let me think, would it be A? Let's see, A, B.
If we're intelligently looking at this, depth first search will look at is the nodes that we can expand from this, is the destination right there? If it is, hop immediately to it. So we can go directly from A to D because it is a direct successor. So that is something else to consider.
All right.
Getting to E, that would just be A to B to E. Or directly A to E if it's something that we can explore directly.
Okay.
So there's a bit of confusion here with regards to what you can do. If we're going directly to D, then we should either directly be able to see it and hop to it. But if that's the case, we should also be able to do that to E, be able to hop directly to it. If we've already explored B completely, getting to C, that's I think what's happening here. We've already explored it. Some initial ones getting to F, A to B to E to F, straightforward, to G. There's a kind of a fast path.
Yeah. Actually. Yeah, the age gets interesting.
So let's see if we can write some pseudocode for depth first search. Takes two parameters, an initial vertex and a target vertex. So we're not looking for the shortest path, we're just looking for a path that depth first search would relate. I don't know if that's actually worth quite trying at the moment, but let's take a look at the pseudocode and kind of map what your thought process would be to what actually happens. So depth first search takes those two parameters, the source vertex and the destination vertex. And you can see that this is very similar to when I talked about tail recursion. There was a public and a private method here. This is just overloaded. DFS here is overloaded with the initial path. When the user calls depth first search, they shouldn't have to provide an additional parameter that is an empty list for the path. So we overload the method. The user calls depth first search without that path. And then that calls the overloaded method that involves an empty path at the beginning as we figure out the path that is taken. The path should start at the source vertex. So we should add the source vertex to the path. We then are going to keep track of this concept of visited nodes, nodes that we've been to before. If there is an outgoing edge from some vertex to a vertex that we've seen before, there's no reason to go back to it. It's already in the recursive chain. We're going to go back to it at some point. There's no reason to add it. If we did that, we could create an infinite loop. Going from A to B to C to A to B to C to A to B to C. If we've seen A before, there's no reason to go to it. We will eventually get back to it if the C and B lead to nothing in the recursive chain. So we mark the source as visited. If the source is the destination, we found the path. If the source and destination are different, for every unvisited neighbor of the source, we're going to recursively call DFS on each unvisited neighbor. So now the source is going to be one of the unvisited neighbors. The destination is still the destination. And the path that we've seen so far is the path that we found. So if that returns that a path is found in some capacity, then this returns that a path is found. If this loop terminates from this initial recursive depth, that means that no path was found from any neighbor of the source node. So no path can exist. So we just do this recursively. Question?
Doesn't this mean that you're just finding a path? Shortest path?
Yes. Yeah, this is just looking for a path. We're not worried about the shortest path. There's a separate algorithm that we will worry about if we're trying to find the shortest path. This is just trying to find, does a path exist? And depth first search is certainly a way to do this. And so we should talk about the benefits and detriments of using this on a graph to find a path between a source and destination. So first thing, if a path exists, this will find it. What's nice about storing this way is very easy to retrieve the path. What is the path that we use to find from source to destination? It's embedded in the path. So we just have to return the path from DFS, and we don't need to store anything else as we go. It's being calculated as we call this. Do note though, as mentioned here, the path that is found is not guaranteed to be the shortest path by any metric. The two metrics we might care about for shortest path are the number of edges or the total edge weight. And if depth first search returns something, we can't state anything about it being the shortest path. So if we ran this depth first search on A to F, it would return A, B, E, F, not A, E, F. So if we look back at the graph, the shortest path from A to F by number of edges is just A to E to F. But depth first search will be exploring these in alphabetical order from this based on some ordering of its neighbors. So it will find A, B, E, F, not A, E, F. But again, it is a path, and sometimes just having a fast answer to does a path exist is important. Questions on depth first search so far? Okay, the other one we might care to look at is breadth first search. Where have we done breadth first search before? Yeah. Yeah, it was in a binary search tree. What kind of traversal is more of a breadth first search? If an in-order traversal was a depth first search, what kind of traversal is a breadth first search? Yeah. Level order is a breadth first search. Yeah, you're looking at level by level, which is the concept of breadth. We're going to explore every node that is distance 1 away from the root, every node that is distance 2 away from the root, every node that is distance 3 away from the root. That level order concept is exactly the concept of breadth first search.
Let me think. There's that. I don't remember here. I recall we did like draw like. Do you remember those early that first homework where we did like early recursion trees and where we drew them and then we looked down level by level. That reminds me of that.
Yeah, that is very similar. So generalizing this to a graph, in general, we want to, starting at the source, look at every neighbor that is 1 step away. Then from everyone there, we're going to look 1 step away from that, 1 step away from that, 1 step away from that. And so we're looking at every node that is 1 edge away, 2 edges away, 3 edges away, very much the same idea of a level order traversal in a tree. So we're going to say for every path that we've looked at so far that doesn't get us to the target vertex, add it to a queue to explore. We're going to then, so we can look at from the root, we're going to add every neighbor to a queue. Then we're going to look at the first one of those. We're going to add every one of its unvisited neighbors to the queue. And we're just going to continue to do that, very much similar to the level order traversal, using a queue and saying for every node in the queue, add its left child and then right child to the queue. And then just repeat this, and the order of the output there is the level order. It's very similar in a graph where we're just adding to a queue every neighbor of the initial vertex. Then for each one of those, we're going to add all of its unvisited neighbors. And for each one of those, we're going to add all of its unvisited neighbors until we reveal the destination. So we'll do nodes earlier in the alphabet first again. So what is the explored sequence of nodes getting from node A to every other node in the graph? Let's do exactly the same thing. And we'll see breadth first what this looks like. So we see getting from A to B is pretty straightforward. We're going to add B and then D and then E to the queue. But the first one we get out of that queue is B, so we're done. To get to C, we're going to add B and then D and then E. When we explore B, we're going to add E, but since it's already in the queue, we don't add it again. When we look at D, we will add G and H. Then we go back to E. Maybe it's worth drawing this as the queue. Probably would help there. So I like to envision a queue kind of like this. We start with adding A to the queue. We're going to explore all of its neighbors in order. As we visit A, we're going to add B and then D and then E. We've now finished A. For B, we're going to add E, but E's already in the queue, so we don't worry about it. For D, we add G and H to explore. For E now, we're going to add F. And then when we see E, that doesn't get anywhere we haven't been before. F's already in there, so that goes away. G adds H, that's already in there. H adds F, that's already in there. F adds C, which is our destination. And that tells us that we got there. What were the nodes that we added on the way to get there? It was A to E to F to C. Were the nodes that we actually expanded that added the next thing that we needed, A to E to F to C to get us to there.
Oh,
So we need to store that as we do this as well in order to be able to reconstruct the path. The path is not inherent in this structure when we find it in the same way it was inherent in the path that we stored with depth first search. So we need to store the path at a recursive depth every time we add something or I guess DQ something from the queue. And we see that there are quite a few, everything in blue here is something that changed from the depth first search order. But what do we notice about how breadth first search is working? What changed here with regards to the results for things that are in blue?
well, it seemed to take, it seemed to leave out like the other nodes that did not follow the pathway to their desired destination.
Yeah, we stored that as we went.
Yeah,
So we found where it differs from breadth first search is when breadth first search didn't return the best answer in terms of the number of edge traversals. So breadth first search actually returns that minimum edge, number of edges path, which is great.
Well, if you broke.
So here's some pseudocode for breadth first search. We start with a queue. We put into that queue the initial vertex. We again mark that as visited. While the queue is not empty, we're going to dequeue from that queue, remove the first element in that queue. If the vertex that is removed from the queue is the destination, yay, we found the path. If not, we're going to, for each unvisited neighbor, mark it as visited and add it to the queue. And then when we dequeue, that has the path. Where is the path stored in this? It's not really, at least not as we can see it right here. So let's take a look at it. We get the shortest path by number of edges. So this does not give us the shortest path by edge weight. We're going to talk about that algorithm in a bit, but breadth first search will always return that shortest path by number of edges. But in the same way that depth first search, we could take advantage of the recursion from that to be able to construct the path. We have to, when we explore it, when we explore a node in the queue, we have to note which node we came from when we explored it, when we added it. So if we go back to this process and redraw how we're calculating this path to C, when we draw out that queue, when we visit B, we're going to have a backtrack to A. When we visit D, there's a backtrack to A. When we visit E, there's a backtrack to A. Because we added each of these to the queue at A. If we look at the code, it says for that vertex, add all of its neighbors to the queue. So B and D and E all get added to the queue at this point. When we explore B and we see that E could be there, we're going to, instead of adding it again, since it's already there, we don't put a backtracking arrow from E back to B. The shorter path is directly back to A. It's one edge instead of two edges. When we expand every other node, we're going to now do D, and G goes back to D, H goes back to D. Then we go to E, E can get to F, that points back to E. H already has something pointing back when we expand G, when we expand H. So it's really when we get to the F that we see the C backtracks here. So the backtracking arrows that we see as we see C, F, B, A, the backtrack is exactly the opposite of the path that we get. So the backtracking path is stored at that point. So we needed a separate structure to store the backtracking, which should remind you of the current assignment. It's very much just one other thing that we are storing as we do this. And we'll find that this is very common in computer science when we need to reconstruct a path, but we're also doing something iteratively rather than recursively necessarily. We need that path, then we'll be storing that path in some capacity. So this is kind of the augmentation that we make to the graph structure to be able to recreate the path once we DQ the C and see that we've reached our destination. Questions about that? Okay. Yeah, for each node in the graph, when we explore it, note which node we came from. Great. We just add to our struct, in this case, for each vertex, we're going to add a previous field, and we're going to store a reference to the node that we came from when we DQ it. And the general trade-off we see between depth first search and breadth first search is that if you've studied these in a prior class, hopefully you know this. If not, it's a good time to learn it. Depth first search uses linear memory. We never are storing more than the depth that we are, how deep we are into this graph. We're never storing more memory than that. Whereas with the queue, we could reasonably be adding, if our source vertex has edges to every possible vertex in the graph, we could be storing all of those vertices in the queue. So the trade-off is less memory for depth first search, but we don't have any guarantee that the result that is returned to us is the optimal result in terms of number of edges. Breadth first search finds that shortest path by number of edges, but has a much larger memory footprint in the worst case. So depending on what you need out of what you're answering, what kind of problem you're answering, and the constraints or limitations, it might make more or less sense to use one of these versus the other. Wow, that's an A and not an S. What are the runtimes of D at S and B at S in terms of the number of vertices and number of edges? What's nice is in terms of time, at least, both run in B plus E. This makes sense, but why not B times E? So this is a good opportunity to kind of look back on and think about why do these run in B plus E, thinking about this asymptotically. There's one assumption that we made in both depth first search and breadth first search that make this a plus and not a times. Yeah.
You've already visited one of the vertices, you don't have it.
Yeah, it's the concept of visited. If we didn't have that concept of visited, then we would need to, for each vertex, look at each possible edge. But once we've looked at an edge and determined is the node that this edge goes to, the destination of this edge, is that already visited and or in the queue already for breadth first search, then we don't add it again. It means that we're, only looking at each vertex and or edge at most once. Once we consider a vertex or an edge, we're not considering it again because it's already been visited or it's already in the queue. So we don't need to do anything with the number of edges for each vertex in the worst case. Which is nice. So we're exploring each node and each edge at most once. Once we explore one, we never need to consider it again. If it's a vertex, it's been marked visited. If it's an edge, then it's something that we considered from the source vertex. So graph search is useful in so many ways. Graphs are probably the most studied structure in computer science. My first advisor in my PhD, my first advisor's husband, who also worked in that department, studied graph theory, which is a large field of theoretical computer science, just looking at how can we improve algorithms that run on graphs? What can we use graphs for? What kinds of new problems can we solve? How can we make those more efficient? So as an example, let's take a look at our wonderful state. by number of edges, what is the shortest way to get to from Seattle to Pullman?
Shortest, A.
This is phone routing towers. So we can imagine that these are relay towers that if you're trying to make a call from one place to another, is going to relay the call through relay centers that are located in each of these places. Yeah, Seattle to
Yeah.
Wenatchee to Spokane to Pullman gets you there in 3 edges.
Shortest edges, that's what you meant by shortest way, right?
Yeah,
Now-
fastest would be something like by distance,
Yeah, let's see, that's Seattle, Cleella, Moses Lake, Richmond, Pullman.
probably, yeah. So now we're looking at the difference between number of edges versus edge weight. The edge weight would be the distance, the actual length of those edges. So they answer very different kinds of problems. But now you can imagine that, and this happens in networking all the time, that Wenatchee's phone exchange goes down. Is it still possible for Seattle to talk to Pullman?
Yes,
It is. There is an additional route that we could now basically take Wenatchee, the vertex, out of this graph. Is there still a simple path from Seattle to Pullman? Yes. If Tacoma's phone exchange goes down, can Olympia talk to Spokane?
nope,
No, there is no way. So these kinds of graphs inform things like if redundancy, if any one of these phone exchanges fails, what portion of this graph is cut off from the rest of the graph or from certain other parts of the graph. So you can do things like use this to do that. And it's very easy to see the effects of kind of leave one vertex out. Here's another graph search. This is some downtown. This is Seattle's downtown. And a bunch of one-ways because large cities have a bunch of one-ways. So these graphs show what streets are two-way and which streets are one-way. We are at 3rd and Pine. Can we get to 1st and University using this graph? Yep, 3rd and Pine, and when I get to 1st and University.
yep,
We can. There exists a simple path. Can we get from 3rd and Pine to 4th and Seneca?
no, you cannot.
We cannot. So we can see via simple path, any search would find this for us. We could use depth first search or breadth first search, and either one would return, yes, you can get there, or no, you can't get there. And in this case, if we use breadth first search, that would be the minimum number of blocks in order to travel from source to destination. It would tell you exactly how to get there. And depth first search would just return a path. It would not take as much memory to come up with that path, but it just tells you, yes, it is possible, no, it isn't possible. There's no guarantee about how long it would take. It could find a ridiculously long path. It could be that my path from the Catalyst building to Spokane Arena is routed through Monaco. Who knows? But depth first search might find that path saying, yes, it is possible. It's going to cost you a ton. So other kinds of search algorithms, these are presented just as a very brief overview because they're useful and relevant to a lot of AI related searches, but also are just usually expansions on breadth first search or depth first search. One is called iterative deepening. So we're going to start to combine the ideas of depth first search and breadth first search. Iterative deepening just says, let's use depth first search, but only up to a maximum depth. What does this do instead of using depth first search or breadth first search? Why would you care to cut off the distance that depth first search can look? Yeah.
The path that you were looking at gets too far, you know.
Yeah, we wanted to get from here to Spokane Arena, we don't want it to route through another country. So we could say, we're only gonna look out so far. If a path exists, it probably exists within this many vertices of here. Don't get off running in the wrong direction and stick with it. We're going to hard code that we know it's within this many edges, or it's likely to be within this many edges. So what we can do is if we fail to find the query, we can increment K and start over. So we depth first search to distance 2, then 3, then 4, then 5, then 6, then 7. And if we increment K as we go like this, what we're really doing is a breadth first search. But we're not using a queue to do it, we're using depth first search, and it's wonderful linear memory. So what's the downside to using iterative deepening? We're kind of getting the benefits of depth first search, linear memory, the benefits of breadth first search in that we're going to find the shortest path if we start small and increment over time. What's the detriment?
Probably the runtime.
The runtime? What is the cap of how much longer iterative deepening could take?
It's pretty exponential, if I'm being honest.
It's not.
So anyway, no.
Compared to breadth, well, it is in that breadth first search is exponential in its, but it's twice as bad. The cap is it will take up to twice as long as breadth first search to find it.
That makes sense.
And I can explain why that is at the start of tomorrow's class because we are out of time. But we'll get to that. I have office hours starting now.
Oh,
I would recommend it. Useful. Let me know.